Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the story of an ancient visitor from the deepest cold and its gravitational dance with Mars. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to all those who've already joined along, thank you. In the furthest reaches of our solar system, where sunlight becomes little more than starlight and temperatures hover just above absolute zero, something stirs. The Oort cloud stretches across a sphere nearly 2 light years in diameter, a vast reservoir of frozen memories from the solar system's birth. Here, countless icy bodies drift in slow, patient orbits, most destined never to approach the Sun closer than Pluto ever ventures. They are the remnants of planetary formation, scattered outward by Jupiter's gravitational violence 4.5 billion years ago, now dwelling in perpetual twilight. Among these frozen wanderers moves 3IATLAS, though it carries no name yet in this distant realm. Its surface holds water ice layered with carbon dioxide and methane, all locked in crystalline stillness for eons beyond counting. This body has traced its vast elliptical path through space so distant that our Sun appears as merely another star in the constellation of lights. The comet's nucleus measures perhaps a few kilometers across, unremarkable among the trillions of similar objects that populate this frozen frontier. Yet something sets it apart, a trajectory that will carry it not just toward the inner solar system, but on a path that speaks to origins even more distant than the Oort cloud itself. The mathematics of orbital mechanics dictate that most comets never leave their frozen realm. They require a gravitational nudge, perhaps from a passing star, or the subtle tug of the galaxy's own structure to begin the long fall inward. What provides this initial push for 3IATLAS remains one of those quiet mysteries that astronomers piece together from computer models and careful observation. The perturbation might have occurred millions of years ago, a stellar encounter so distant that the passing star has long since moved beyond our local stellar neighbourhood, or perhaps the comet's orbit was shaped by the cumulative influence of countless smaller gravitational interactions, each one imperceptible but adding up over geological time to produce this single, decisive journey sunwards. As 3IATLAS begins its migration from the outer darkness, it moves with the patience that defines all celestial mechanics. Its initial velocity measures perhaps a few hundred meters per second, barely faster than sound travels through Earth's atmosphere. This seems impossibly slow for something crossing interplanetary space. Yet the comet has billions of miles to fall, and gravity's influence grows stronger with each passing year. The Sun's gravitational well extends far beyond the orbit of Neptune, its influence felt even in the Oort cloud's distant realm, though weakened by distance to barely a whisper of its strength near Earth. For the first million years of its inward journey, 3IATLAS shows no visible signs of activity. Its surface remains locked in the same frozen state that has preserved it since the solar system's formation. The temperature hovers around 10 Kelvin, so cold that even the hardiest molecular bonds barely vibrate. This is a realm where the familiar physics of terrestrial experience break down, where gases become solid and solid materials exhibit behaviours alien to our everyday understanding. The comet's gravity, weak as it is, holds its icy constituents in place, but only just. A human standing on its surface, if such a thing were possible, would find that a gentle jump might launch them into permanent orbit around this tiny world. The first signs of change come gradually, as they must in the realm of astronomical phenomena. When 3IATLAS crosses the orbit of Neptune, still more than 2 billion miles from the Sun, solar radiation finally becomes strong enough to begin sublimating the most volatile compounds on its surface. This process happens with geological slowness at first. Individual molecules breaking free from the ice matrix and drifting away into space. The comet begins to develop what astronomers call a coma, a tenuous atmosphere of gas and dust that will grow more pronounced as the journey continues. What strikes observers as remarkable is how this ancient visitor seems to know precisely where it's going. Of course, the comet possesses no consciousness, no intent or purpose in the biological sense, yet its trajectory displays the kind of mathematical precision that suggests deeper forces at work. The gravitational influences that shaped its path operate according to principles that remained hidden from human understanding until Newton codified them 3 centuries ago. Yet they have been guiding celestial bodies along their appointed paths for billions of years before our species evolved the capacity to observe them. As 3IATLAS continues its approach, astronomers begin to calculate its orbital elements with increasing precision. The numbers tell a story that becomes more intriguing with each observation. This visitor's trajectory suggests an origin not just from the Oort cloud, but from even further afield, possibly from interstellar space itself. Its orbital inclination and eccentricity hint at a past that precedes our solar system's current configuration. When the gravitational architecture of planets and asteroids existed in different arrangements, the comet carries within its frozen matrix a chemical signature of conditions that prevailed during the earliest epochs of planetary formation. Water ice mixed with organic compounds, trace elements that formed in the cooling gas cloud that gave birth to our Sun and its family of worlds. As 3IATLAS approaches the inner solar system, it becomes a time capsule opening in slow motion, releasing molecules that have remained unchanged since before Earth's formation. These ancient volatiles will eventually stream away from the comet's nucleus, creating the spectacular tail that makes such visitors visible to human observers. But the most intriguing aspect of 3IATLAS lies not in its composition or its origin, but in its destination. Orbital calculations reveal that this ancient wanderer will pass remarkably close to Mars during its passage through the inner solar system, not close enough to pose any threat to the red planet, but near enough for their gravitational fields to interact in ways that will subtly influence both objects' future paths. This celestial encounter, predetermined by the mathematical laws that govern orbital mechanics, represents a conversation between 2 very different worlds, one ancient and icy, the other dusty and terrestrial, both carrying information about the solar system's deep past. The dance between comet and planet will unfold over months, a gravitational ballet choreographed by forces that operate across scales from the quantum to the cosmic. As 3IATLAS approaches its rendezvous with Mars, it continues to brighten and develop the characteristic features that make comets among the most beautiful objects in the night sky. Yet beneath this visible spectacle lies a deeper story about how gravity shapes the architecture of our solar system, how ancient visitors from the outer darkness can carry information across billions of years, and how even the most distant objects remain connected by invisible threads of gravitational influence. The comet's approach toward Mars represents more than just another astronomical event. It embodies the principle that nothing in the universe exists in isolation, that even objects separated by billions of miles and billions of years remain connected through the fundamental forces that govern cosmic evolution. Soon, this visitor from the deep cold will reveal what secrets it carries and what subtle changes its presence will bring to the red planet's ancient, patient orbit around our life-giving sun. Beyond the orbit of Uranus, where sunlight carries only 1/400th the warmth it provides to Earth, 3IATLAS begins its transformation from dormant ice ball to active comet. The process unfolds with the measured pace that characterizes all astronomical phenomena, each step following the inexorable laws of physics that have governed such transformations since the solar system's birth. What appears to human observers as a sudden brightening actually represents the culmination of processes that began when the comet first stirred from its distant orbit, millions of years and billions of miles ago. The Sun's influence reaches across interplanetary space not just as gravity, but as a constant stream of electromagnetic radiation. Even at distances where Earth appears as nothing more than a pale blue dot, solar photons carry enough energy to begin breaking the molecular bonds that have held the comet's surface materials in frozen stasis. Water ice, the most abundant component of 3IATLAS, remains stable at these temperatures, but more volatile substances begin to respond to the gradually increasing solar flux. Carbon dioxide ice, frozen harder than steel in the Oort cloud's depths, starts to sublimate directly from solid to gas, bypassing the liquid phase entirely in the vacuum of space. This sublimation process creates the first whisper of the comet's coma, an atmosphere so tenuous that it would register as perfect vacuum by terrestrial standards. Yet this gossamer envelope of gas and dust represents the comet's awakening, the first sign that 3IATLAS has begun its conversation with the inner solar system. The newly liberated molecules carry with them microscopic particles of dust, rocky grains that have remained embedded in the ice matrix since the solar nebula's collapse 4.5 billion years ago. These particles reflect sunlight with an efficiency that transforms them into tiny beacons, making the comet detectable to Earth-based telescopes despite its vast distance. The physics governing this transformation operate according to principles that remained mysterious to astronomers until relatively recently. As gas molecules escape the comet's weak gravitational field, they carry away both momentum and thermal energy, creating a subtle rocket effect that can alter the comet's trajectory by measurable amounts over long periods. This outgassing doesn't occur uniformly across the nucleus surface. Instead, it concentrates in regions where the ice composition varies, or where the nucleus rotation brings different areas into sunlight. The result creates jets of material streaming away from specific locations, giving each comet a unique pattern of activity as individual as a fingerprint. Temperature gradients across the nucleus surface create a landscape of thermodynamic contrasts invisible to the human eye, but crucial to understanding the comet's behavior. Areas facing the sun warm to perhaps negative 150 degrees Celsius, still brutally cold by Earth standards, but warm enough to drive vigorous sublimation. Meanwhile, regions in perpetual shadow remain locked near absolute zero, preserving pristine samples of the solar system's earliest materials. This temperature differential creates thermal stress within the nucleus, occasionally causing chunks of material to break away and join the growing coma as house-sized boulders tumbling slowly through space as 3IATLAS continues its sunward journey, crossing the orbit of Saturn and then Jupiter. the rate of sublimation accelerates according to well-established mathematical relationships. The amount of material escaping the nucleus increases roughly exponentially with the decreasing distance to the Sun, following what astronomers call Whipple's icy conglomerate model. Fred Whipple first proposed this description of comet nuclei in the 1950s, envisioning them as dirty snowballs, composed primarily of water ice mixed with rocky debris. Subsequent observations have refined this picture, revealing nuclei to be more like snowy dirt balls, with lower ice content than originally suspected. But the fundamental physics of solar heating driving sublimation remains unchanged. The growing coma begins to exhibit structure as it expands, shaped by the comet's rotation and the varying composition of materials escaping from different regions of the nucleus. Spectroscopic analysis reveals the presence of water vapor, carbon dioxide, carbon monoxide, and trace amounts of more complex organic molecules. These signatures provide a chemical archaeology of the early solar system, preserving ratios of isotopes and molecular compounds that offer clues about the temperature and pressure conditions that prevail during planetary formation. Each detected spectral line represents a message from the past, encoded in the quantum mechanical properties of atoms and molecules that have remained unchanged for billions of years. The comet's brightness increases not just from growing sublimation, but from the expanding cross-sectional area of its coma. What began as a nucleus perhaps 5 kilometers across now presents an effective target hundreds of thousands of kilometers in diameter to incoming solar radiation. This vast, tenuous atmosphere scatters sunlight like morning fog, creating the fuzzy appearance that gives comets their name from the Greek word for hair. The coma's density remains incredibly low, with particle concentrations that would be considered a hard vacuum in any terrestrial laboratory, yet its sheer size makes it visible across interplanetary distances. Solar wind begins to play an increasingly important role as 3IATLAS approaches the inner solar system. This stream of charged particles flowing outward from the Sun at speeds of several hundred kilometers per second interacts with the comet's expanding atmosphere in ways that will eventually create the spectacular tale that makes such visitors memorable to human observers. The solar wind carries embedded magnetic fields that become entangled with ionized molecules in the coma, creating complex magnetohydrodynamic interactions that channel escaping material into narrow streams pointing away from the Sun. Deep within the nucleus, processes invisible to external observation begin to reshape the comet's internal structure. As surface layers sublimate away, they expose fresh material beneath, creating a constantly changing landscape of cliffs, valleys, and plains sculpted by the differential escape of volatiles. Some regions develop protective crusts where dust accumulates faster than it can be blown away by outgassing, creating dark patches that absorb solar radiation more efficiently and drive localized heating. Other areas develop into active regions where jets of material stream away with velocities measured in hundreds of meters per second. The comet's rotation, probably established during its formation billions of years ago, creates a day-night cycle that modulates the intensity of sublimation across its surface. Most comets rotate with periods measured in hours to days, far faster than the timescales over which significant sublimation occurs. This rapid rotation helps distribute solar heating more evenly than would occur if the same hemisphere always faced the Sun, preventing the development of extreme temperature gradients that might fragment the nucleus entirely. As 3IATLAS approaches the asteroid belt, its transformation accelerates towards the moment when it will become visible to naked-eye observers on Earth. The mathematical precision of its trajectory remains unchanged despite the growing complexity of forces acting upon it. Gravitational perturbations from Jupiter and Saturn have been incorporated into its path over millions of years. while the subtle rocket effects of asymmetric outgassing create tiny course corrections that accumulate over time. Yet the fundamental orbital elements that will carry this ancient visitor past Mars remain locked into the geometry of space and time, predetermined by the initial conditions that set the comet on its current path eons ago. The beauty of this transformation lies not just in its visual spectacle, but in how it demonstrates the interconnected nature of physical processes across vast scales of space and time. Quantum mechanical properties of individual molecules drive bulk sublimation that creates observable phenomena across millions of kilometers. The same gravitational forces that hold galaxies together guide this small visitor along its appointed path through our solar system, and the chemical signatures preserved in its ice carry information about stellar nucleosynthesis that occurred before our sun ignited, connecting this moment to the deep history of cosmic evolution. Soon, 3IATLAS will cross the orbit of Mars, bringing it into the realm where terrestrial planets dominate the gravitational architecture of local space. The encounter that awaits will demonstrate how even brief passages can create lasting changes in the orbital mechanics that govern our solar system's future evolution. Jupiter hangs in space like a gravitational lighthouse, its immense mass warping the fabric of space-time across billions of cubic kilometers from 3IATLAS, still millions of miles away. The gas giant appears as nothing more than a bright star among many others scattered across the cosmic dark, yet its influence reaches across interplanetary distances with mathematical precision, shaping the trajectory of every object that ventures into its domain. The comet feels this pull as a gentle acceleration, measurable only by the most sensitive instruments, but persistent enough to alter its path in ways that will echo through the remainder of its solar system passage. The physics of gravitational encounters between celestial bodies follows principles that remained hidden from human understanding until Johannes Kepler decoded the elliptical nature of planetary orbits and Isaac Newton revealed the inverse square law that governs attractive forces. Yet these same principles have been orchestrating cosmic choreography since the first condensations of matter began collapsing under their own gravity in the primordial universe. Jupiter's gravitational field extends infinitely into space, weakening with distance but never entirely disappearing, creating what astronomers call a sphere of influence that encompasses much of the outer solar system. As 3IATLAS approaches its closest point to Jupiter, still far beyond the orbits of the Galilean moons, the mathematics of orbital mechanics dictate a precise exchange of energy and momentum. The comet's velocity increases as it falls into the planet's gravitational well, reaching maximum speed at the moment of closest approach before slowing again as it climbs back out toward interplanetary space. This gravitational slingshot effect demonstrates one of the most elegant principles in celestial mechanics: energy conservation operating on astronomical scales, where the total energy of the system remains constant even as individual components trade kinetic and potential energy back and forth. The encounter unfolds over months, though the most significant gravitational effects concentrate into a period of weeks surrounding closest approach. During this time, Jupiter's gravitational field deflects the comet's trajectory by a few degrees, an angular change so small as to be nearly imperceptible to casual observation, yet profound in its long-term consequences. This deflection alters not just the comet's direction of travel, but also its orbital inclination relative to the plane of the solar system, creating a three-dimensional trajectory that carries it toward an eventual encounter with Mars along a path that would not have existed without Jupiter's gravitational intervention. The gas giant itself experiences an equal and opposite reaction, according to Newton's third law, though the effect remains vanishingly small due to Jupiter's enormous mass advantage. The planet's orbital velocity changes by perhaps a few micrometers per second, a perturbation so tiny that it would require centuries of precise measurement to detect. Yet this exchange demonstrates the fundamental reciprocity that characterizes all gravitational interactions. Every force creates an equal and opposite response. Every orbital deflection involves a mutual exchange of momentum. Even when the masses involved differ by factors of trillions, Jupiter's influence on 3IATLAS represents just one example of the complex gravitational architecture that shapes trajectories throughout the solar system. The gas giant serves as a cosmic traffic director, deflecting some comets back toward the outer solar system while accelerating others toward the inner planets. This same gravitational shepherding has been operating for billions of years, gradually clearing debris from certain orbital zones while concentrating it in others, creating the relatively stable configuration of planets and asteroids that characterizes our solar system today. The timing of this encounter reveals another layer of cosmic choreography that operates across geological timescales. Jupiter completes one orbit around the Sun every 11.86 Earth years, while 3IATLAS follows its elongated elliptical path on a schedule measured in millions of years. The alignment that brings these two objects into gravitational contact represents a convergence of orbital periods that was established when the solar system achieved its current configuration billions of years ago. Had the comet begun its inward journey even a few thousand years earlier or later, it might have missed this gravitational encounter entirely, following a completely different trajectory through the inner solar system. The mathematical precision required to predict such encounters challenges human intuition about the nature of cosmic coincidence. When astronomers first calculated 3IATLAS's orbit, they discovered that its path would carry it remarkably close to Mars during its passage through the inner solar system. This proximity results directly from the gravitational nudge provided by Jupiter, demonstrating how perturbations that occur in the outer solar system can influence events that unfold much closer to the Sun. The interconnected nature of gravitational influences means that no celestial encounter occurs in isolation. Each represents the culmination of forces that have been building across vast expanses of space and time. The comet's passage through Jupiter's gravitational domain also provides astronomers with opportunities to refine their understanding of the gas giant's mass and internal structure. Precise measurements of how 3IATLAS's trajectory changes during the encounter allow scientists to calculate Jupiter's gravitational parameter with increased accuracy, contributing to models of the planet's composition and the distribution of mass within its interior. These observations demonstrate how celestial mechanics serves as a tool for exploring the physical properties of objects too distant for direct examination. Solar-wind interactions complicate the gravitational dynamics as 3IATLAS approaches the inner solar system. Jupiter possesses a powerful magnetosphere that deflects charged particles streaming outward from the Sun, creating a bow shock wave that extends millions of kilometers into space. As the comet passes through this magnetized environment, its growing coma of ionized gases experiences forces that operate independently of gravity, creating subtle perturbations that must be accounted for in trajectory calculations. These electromagnetic effects remain small compared to gravitational influences, but they illustrate the multiple types of physical interactions that shape the motion of objects moving through interplanetary space. The gas giant's system of moons adds another layer of gravitational complexity to the encounter. Europa, Ganymede, Callisto, and Io trace their own orbital paths around Jupiter, each contributing minute gravitational perturbations that influence the comet's trajectory. These effects operate according to the same inverse square law that governs planetary interactions, but scaled down according to the smaller masses involved. The cumulative influence of all 4 Galilean moons creates a gravitational environment that varies with their orbital positions, introducing subtle variations in the forces acting on 3IATLAS as it passes through the Jovian system. Deep within Jupiter's hydrogen-helium atmosphere, convection currents driven by the planet's internal heat create weather patterns that dwarf anything experienced on terrestrial worlds. The Great Red Spot, a storm system larger than Earth that has persisted for centuries, represents just one visible manifestation of the dynamic atmospheric processes that characterize gas giant planets. Yet from 3I-ATLAS's perspective, these atmospheric phenomena remain invisible and irrelevant. The comet responds only to Jupiter's gravitational field, which depends solely on the planet's mass and distance, remaining unchanged regardless of the atmospheric turbulence occurring within the gas giant's interior. As 3I-ATLAS exits Jupiter's gravitational domain and continues its journey toward the inner solar system, it carries with it a new trajectory that will determine all its subsequent encounters. The gravitational nudge provided by the gas giant has set the comet on a course that will carry it past Mars at a distance of just a few million kilometers, close enough for significant gravitational interaction between these two very different worlds. This predetermined encounter represents the next movement in a cosmic symphony that began when the comet first stirred from its distant orbit millions of years ago, each gravitational interaction building upon the last to create a trajectory of mathematical elegance and physical inevitability. The beauty of celestial mechanics lies in how it demonstrates the universe's fundamental orderliness beneath apparent chaos, revealing how the same physical laws that govern the fall of an apple also determine the paths of comets across interplanetary space. Mars traces its ancient path around the Sun with the patience that defines all planetary motion, completing each elliptical orbit in 687 Earth days. The red planet's dance through space follows the same mathematical principles that govern all celestial mechanics, yet its particular orbital characteristics create a rhythm uniquely its own. Unlike Earth's nearly circular path, Mars follows a more elongated ellipse that carries it as close as 207 million kilometers to the Sun at perihelion, and as far as 249 million kilometers at aphelion. This orbital eccentricity creates seasonal variations that stretch across Martian years, with each hemisphere experiencing summers and winters of dramatically different lengths and intensities. The planet's orbital inclination tilts its axis 25 degrees relative to the plane of its orbit, remarkably similar to Earth's 23.5-degree tilt. This axial orientation ensures that Mars experiences seasons much as our own world does, though each season lasts nearly twice as long due to the planet's longer orbital period. Currently, Mars approaches the portion of its orbit that will bring it into gravitational contact with 3IATLAS, an encounter predetermined by the mathematical relationships between orbital periods, inclinations, and the three-dimensional geometry of interplanetary space. The precision required for such celestial encounters challenges human comprehension of cosmic coincidence. Mars completes roughly one orbit for every 2 Earth years, while 3I-ATLAS follows its elongated path on a timescale measured in millions of terrestrial years. The alignment that will bring these objects into close proximity represents a convergence of orbital mechanics that was established when the solar system achieved its current configuration. The comet's trajectory, modified by its recent encounter with Jupiter's gravitational field, now carries it along a path that will intersect Mars's orbital zone at precisely the moment when the planet occupies that same region of space. Atmospheric dynamics on Mars operate according to principles fundamentally different from those that drive weather patterns on Earth. the planet's thin atmosphere, composed primarily of carbon dioxide with trace amounts of nitrogen and argon, maintains surface pressures less than 1% of Earth's sea level density. This tenuous envelope provides little greenhouse warming, allowing surface temperatures to vary dramatically between day and night, between seasons, and between equatorial and polar regions. During southern hemisphere summer, when Mars reaches perihelion and receives maximum solar heating, temperatures near the equator can briefly approach the freezing point of water. During winter at the poles, carbon dioxide itself freezes out of the atmosphere, creating seasonal ice caps that advance and retreat with the planet's orbital rhythm. Dust storms represent one of Mars' most distinctive atmospheric phenomena, ranging from localized dust devils that last minutes to planet-encompassing tempests that can persist for months. These storms arise from the interaction between solar heating, topographic features, and the planet's rapid rotation. Mars completes one rotation every 24 hours and 37 minutes, creating a day-night cycle remarkably similar to Earth's. This rotational period drives atmospheric circulation patterns that transport dust particles across vast distances, occasionally creating storms visible from Earth-based telescopes as changes in the planet's apparent brightness and colour. The planet's internal structure reflects its formation history as one of the smaller terrestrial planets that condensed from the solar nebula 4.5 billion years ago. Mars possesses a partially molten iron core surrounded by a silicate mantle and a basaltic crust that averages perhaps 50 kilometers in thickness. Unlike Earth, Mars lacks a strong magnetic field. Having lost its global magnetosphere billions of years ago, when its core began to cool and solidify. Remnant magnetic fields preserved in ancient crustal rocks provide evidence of this lost magnetosphere, creating a patchwork of magnetic anomalies scattered across the planet's southern highlands. Olympus Mons rises from Mars's western hemisphere as the largest volcanic mountain in the solar system, its summit reaching 21 kilometers above the surrounding plains. This enormous shield volcano formed through millions of years of effusive eruptions. Building layer upon layer of basaltic lava flows into a structure that dwarfs any terrestrial mountain. The volcano's massive bulk creates local gravitational anomalies measurable by orbiting spacecraft, contributing to the complex gravitational field that will influence 3IATLAS during its upcoming close approach. Though Olympus Mons appears dormant today, geological evidence suggests it remained active until relatively recently in geological terms, perhaps as recently as 2 million years ago. The planet's two small moons, Phobos and Deimos, trace rapid orbits around their parent world with periods measured in hours rather than days. Phobos, the larger and closer of the two, completes 3 orbits during each Martian day, rising in the west and setting in the east as seen from the planet's surface. These moons likely represent captured asteroids, rocky bodies that wandered too close to Mars and became gravitationally bound to the planet sometime after its formation. Their irregular shapes and dark carbon-rich surfaces support this origin hypothesis, though the precise mechanism of their capture remains one of those quiet mysteries that planetary scientists continue to investigate. Martian geology tells a story of dramatic climate changes that unfolded over billions of years. Ancient riverbeds carved into the planet's southern highlands provide evidence of flowing liquid water during Mars' earliest epoch, when the atmosphere was thicker and greenhouse warming kept surface temperatures above the freezing point. These channels wind across hundreds of kilometers, creating drainage patterns that mirror those formed by rivers on Earth. Yet this wet period ended more than 3 billion years ago, when Mars lost much of its atmosphere to space due to solar wind erosion and the planet's weak magnetic field. Polar ice caps composed of water ice and frozen carbon dioxide create seasonal variations in atmospheric pressure as they advance and retreat with Mars' orbital rhythm. During southern hemisphere spring, carbon dioxide ice sublimes directly from solid to gas, releasing millions of tons of material into the atmosphere and increasing global atmospheric pressure by measurable amounts. This seasonal cycle demonstrates how Mars's thin atmosphere responds dramatically to relatively small changes in solar heating, creating pressure variations that would be barely detectable on Earth but represent significant atmospheric perturbations on the red planet. The planet's current position in its orbit places it in the ideal location to experience gravitational interaction with 3IATLAS as the comet completes its passage through the inner solar system. This encounter was not planned by any conscious intelligence, yet it unfolds with mathematical precision determined by the orbital elements established when both objects assume their current trajectories. Mars approaches the point in space where the comet's path will carry it closest to the red planet, setting the stage for a gravitational dance that will subtly influence both objects' future orbits. Surface features on Mars preserve a detailed record of the planet's geological evolution, from the ancient impact craters that scar the southern highlands to the massive canyon system of Valle Marineris that stretches across nearly a quarter of the planet's circumference. These geological formations serve as silent witnesses to the environmental changes that transformed Mars from a world that might have harbored liquid water oceans to the cold, dry planet we observe today. Soon, these same ancient landscapes will experience the subtle gravitational influence of an ancient visitor from the outer solar system, adding another chapter to the red planet's long geological history. The approaching encounter between Mars and 3IATLAS represents more than just another astronomical event. It embodies the principle that celestial mechanics operates with perfect mathematical precision across scales from planetary orbits to galactic rotation, demonstrating how the same physical laws that govern the motion of molecules also determine the paths of worlds through space. Across observatories scattered around Earth's surface and in orbit above its atmosphere, astronomers track the approaching convergence with instruments capable of measuring distances across interplanetary space to within a few kilometers. The calculations that determine 3IATLAS's closest approach to Mars represent one of humanity's most precise applications of celestial mechanics, requiring computer models that account for gravitational influences from every significant body in the solar system. Each measurement refines the predicted encounter geometry, revealing a mathematical ballet choreographed by forces that operate according to principles unchanged since Newton first described the inverse square law of gravitational attraction. The current best estimate places the moment of closest approach at approximately 2.7 million kilometers, a distance that seems vast by terrestrial standards, yet represents remarkable proximity in astronomical terms. This separation equals roughly 7 times the distance between Earth and its moon, close enough for Mars and the Comet to experience measurable gravitational interaction, but far enough to prevent any possibility of collision. The precision of this prediction demonstrates how thoroughly astronomers understand the mechanics of orbital motion, transforming observations of position and velocity into forecasts of future encounters with accuracy measured in minutes and kilometers across millions of miles of space. Velocity calculations reveal the dynamic nature of this cosmic encounter with mathematical elegance. At the moment of closest approach, 3IATLAS will be travelling at approximately 42 kilometers per second relative to the Sun, while Mars maintains its orbital velocity of 24 kilometers per second along its elliptical path. The relative velocity between comet and planet at closest approach will reach nearly 30 kilometers per second, fast enough to cross the continental United States in less than 2 minutes. Yet this tremendous speed represents just another variable in the equations that govern gravitational interactions, incorporated into models that predict how the encounter will unfold across weeks of mutual approach and recession. The three-dimensional geometry of the encounter adds layers of complexity that challenge even sophisticated computer simulations. Both objects move through space along curved trajectories that exist in 3 dimensions, with orbital planes inclined at different angles relative to the solar system's fundamental reference frame. 3IATLAS approaches Mars from above the plane of the planet's orbit, creating an encounter geometry that resembles 2 ships passing at sea, rather than a head-on collision. This oblique approach angle ensures that the gravitational interaction will occur gradually, building to maximum intensity at closest approach before diminishing as the objects separate along their respective paths. Gravitational mechanics dictate that both Mars and 3IATLAS will experience equal and opposite forces during their encounter, though the effects manifest very differently due to their vastly different masses. Mars, with a mass approximately 6.4 times 10 to the 23rd kilograms, will experience orbital perturbations measurable only by the most sensitive instruments. The planet's orbital velocity might change by a few millimeters per second, an effect so small that it would require years of precise tracking to confirm through observation. Meanwhile, 3IATLAS, with a mass perhaps 1 billion times smaller, will experience proportionally larger changes to its trajectory and velocity. The comet's orbital elements will undergo subtle but permanent modifications during the encounter. Its orbital period, currently measured in millions of years, might change by thousands of years due to the gravitational interaction with Mars. The comet's orbital inclination and eccentricity will also shift slightly, altering the 3-dimensional shape of its path through space in ways that will influence its future encounters with other solar system bodies. These changes demonstrate how single gravitational encounters can have consequences that echo across geological timescales, creating ripple effects that propagate through the solar system's gravitational architecture for eons after the initial interaction concludes. Advanced computer simulations model the encounter using numerical integration techniques that solve the equations of motion for both objects simultaneously. These calculations must account for the gravitational influences of all major planets, the pressure effects of solar radiation, and the subtle rocket forces created by asymmetric outgassing from the comet's nucleus. The most sophisticated models incorporate general relativistic corrections that account for the curvature of spacetime near massive objects. Though these effects remain negligible for this particular encounter, the resulting predictions achieve accuracy that would have seemed impossible to astronomers working just a century ago. Observational campaigns coordinate telescopes across multiple continents to track both objects throughout the encounter period. Radio telescopes measure the Doppler shifts in reflected radar signals bounced off the comet's nucleus, providing direct measurements of its velocity and distance with extraordinary precision. Optical telescopes track position changes against the background stars, while infrared instruments monitor thermal emissions that reveal information about the comet's composition and internal structure. Space-based observatories contribute observations uncontaminated by Earth's atmospheric turbulence, adding precision to measurements that ground-based instruments cannot achieve. The mathematical framework used to predict the encounter relies on principles established centuries ago, but implemented using computational tools that can solve equations too complex for analytical solution. Newton's laws of motion and universal gravitation provide the fundamental physics, while Kepler's laws describe the elliptical geometries that characterize planetary orbits. Modern orbital mechanics adds relativistic corrections, non-gravitational forces, and numerical techniques that allow astronomers to model systems involving multiple interacting bodies with arbitrary precision given sufficient computational resources. Uncertainty analysis reveals the limitations inherent in any astronomical prediction. No matter how sophisticated the modelling techniques employed, small uncertainties in the initial positions and velocities of both objects propagate through the calculations, creating confidence intervals around the predicted closest approach distance and timing. These uncertainties shrink as additional observations refine the orbital elements, but they never disappear entirely due to the chaotic nature of gravitational systems involving multiple bodies. The current predictions carry uncertainties of perhaps a few thousand kilometers in distance and several minutes in timing. Remarkable precision given the complexity of the calculations involved. Professional and amateur astronomers around the world prepare observing campaigns to document the encounter from multiple perspectives simultaneously. This coordinated effort will generate datasets that extend far beyond the requirements for basic trajectory prediction, providing opportunities to study the comet's physical properties, its response to changing solar illumination, and the subtle ways that gravitational interactions influence the behavior of small solar system bodies. The encounter offers a natural experiment in celestial mechanics, allowing scientists to test theoretical predictions against observed reality with unprecedented precision. The approaching closest approach represents a moment of convergence between two very different types of solar system objects, each carrying information about different epochs in cosmic history. Mars preserves evidence of planetary formation and early atmospheric evolution in its geological features and isotopic composition. 3IATLAS carries chemical signatures of conditions that prevailed in the outer solar system during its formation, potentially including materials that predate the solar system's current configuration. Their gravitational encounter creates an opportunity for these separate historical records to interact, exchanging momentum and energy in ways that will influence their future evolution through space. The precision of modern astronomical prediction transforms what ancient observers would have seen as random celestial wandering into a deterministic dance governed by mathematical relationships of extraordinary elegance and complexity. The encounter between Mars and 3IATLAS demonstrates how thoroughly human understanding of gravitational mechanics has evolved, allowing astronomers to predict cosmic events with accuracy that rivals the precision of atomic clocks. In the vast emptiness between Mars and 3IATLAS, gravitational forces begin their subtle conversation across millions of kilometers of space. These forces operate according to Newton's inverse square law, weakening with distance but never entirely disappearing, creating an invisible architecture that connects every massive object in the universe through threads of mutual attraction. At 2.7 million kilometers separation, the gravitational pull between comet and planet remains vanishingly weak by terrestrial standards, yet measurable by instruments sensitive enough to detect accelerations smaller than those experienced by falling dust motes in Earth's atmosphere. The mathematics of gravitational interaction describe a universe where every particle of matter influences every other particle, regardless of the distances involved. Or Mars, with its mass of 6.4 times 10 to the 23rd kilogram, creates a gravitational field that extends infinitely into space, though its strength diminishes as the inverse square of distance. At the comet's current position, this field produces an acceleration of perhaps a few micrometers per second squared, barely detectable even by the most sensitive instruments, yet sufficient to alter 3IATLAS's trajectory in measurable ways over the weeks surrounding closest approach. The comet's own gravitational field, weaker by factors of billions due to its small mass, exerts an equally real but nearly imperceptible influence on Mars. This reciprocal attraction demonstrates one of the most profound principles in physics: the absolute equality of action and reaction forces, regardless of the masses involved. Every gravitational interaction involves mutual influence, with both objects accelerating toward their common center of mass according to the same fundamental law that governs the motion of planets around stars and stars around galactic centers. As the distance between Mars and 3I-ATLAS decreases, the gravitational force increases according to precise mathematical relationships that allow astronomers to predict the encounter's evolution with extraordinary accuracy. The force doubles when the separation distance halves, quadruples when the distance decreases by half again, following an exponential progression that ensures the most significant gravitational effects concentrate into the hours immediately surrounding closest approach. This nonlinear relationship between distance and force creates encounter dynamics that build gradually over months before reaching maximum intensity in a brief period of mutual proximity. The three-dimensional nature of gravitational attraction adds complexity that requires sophisticated mathematical treatment to fully understand, unlike the simplified two-body problems that provide intuitive understanding of orbital mechanics. The Mars 3I-ATLAS encounter involves gravitational influences from the Sun, Jupiter, and other planets that create a complex web of intersecting force fields. Each gravitational source contributes its own acceleration vector, with the net result determined by vector addition of forces that point in different directions through three-dimensional space. Angular momentum conservation governs how the encounter will unfold, ensuring that certain orbital characteristics remain unchanged even as others undergo modification. The total angular momentum of the Mars Comet system must remain constant throughout the interaction, though individual components can exchange angular momentum between rotational and orbital motion. This conservation law constrains the possible outcomes of the encounter, ruling out certain types of orbital changes while making others inevitable given the initial conditions and approach geometry. Energy conservation provides another fundamental constraint on the encounter dynamics, dictating that kinetic and potential energy can transform into each other but cannot be created or destroyed. As 3I-ATLAS approaches Mars, it gains kinetic energy while losing gravitational potential energy, accelerating as it falls deeper into the planet's gravitational well. After closest approach, this process reverses, with kinetic energy converting back to potential energy as the comet climbs out of Mars's gravitational influence and returns to interplanetary space. The concept of gravitational binding energy helps quantify the strength of interaction between the two objects during their encounter. This binding energy reaches maximum magnitude at closest approach, when the gravitational potential energy of the system achieves its most negative value. Though neither object becomes gravitationally bound to the other, the temporary increase in binding energy during the encounter represents a measurable change in the total energy budget of the local gravitational environment. Tidal forces, though negligible for this particular encounter, illustrate another aspect of gravitational interaction that becomes important when objects approach more closely. These forces arise from the variation in gravitational field strength across the finite size of extended objects, creating differential accelerations that can deform or even disrupt bodies that venture too close to massive companions. For 3I-ATLAS and Mars, separated by the millions of kilometers, tidal effects remain far too weak to influence either object's internal structure, but the same physics governs more dramatic encounters between comets and planets throughout the solar system. The encounter demonstrates how gravitational interactions can transfer energy and angular momentum between different components of the solar system without violating any conservation laws. Mars will gain a tiny amount of orbital energy during the interaction, slightly increasing its orbital radius and period around the Sun. Meanwhile, 3IATLAS will experience changes to its orbital elements that depend on the precise geometry of the encounter, potentially gaining or losing orbital energy depending on whether it approaches Mars from behind or ahead in the planet's orbital motion. Perturbation theory provides the mathematical framework for calculating how gravitational encounters modify orbital elements over time. These calculations treat the encounter as a temporary departure from pure Keplerian motion, with the gravitational influence of Mars creating perturbations that alter the comet's orbital eccentricity, inclination, and orientation in space. The magnitude of these perturbations depends on the masses involved, the minimum separation distance, and the relative velocities at closest approach, all factors that combine according to well-established mathematical relationships. Computer simulations model the encounter using numerical integration techniques that solve the equations of motion with precision impossible to achieve through analytical methods alone. These calculations step forward through time in tiny increments, computing the gravitational acceleration experienced by each object at every moment and updating their positions and velocities accordingly. The most sophisticated simulations can track the encounter dynamics with temporal resolution measured in seconds and spatial precision measured in meters, revealing details of the gravitational interaction that would otherwise remain hidden. The gravitational conversation between Mars and 3IATLAS unfolds according to physical laws that operate with perfect consistency across scales from subatomic particles to galactic superclusters. The same inverse square relationship that describes the attraction between these two solar system bodies also governs the behavior of binary star systems, the orbital mechanics of planetary satellites, and the large-scale structure of the cosmic web that connects galaxies across billions of light-years. This universality of gravitational physics demonstrates the fundamental unity that underlies apparently diverse astronomical phenomena. As the encounter progresses toward closest approach, the gravitational choreography between Mars and 3IATLAS reveals the elegant mathematical relationships that govern celestial mechanics. Each force creates an equal and opposite reaction. Each energy transfer occurs according to conservation laws, and each orbital modification follows from the inexorable logic of Newton's equations of motion applied to the curved geometry of spacetime around massive objects. The beauty of this gravitational dance lies not in any conscious intention or design, but in the mathematical precision with which physical laws translate initial conditions into inevitable outcomes, creating a cosmic ballet of extraordinary complexity that unfolds with the reliability of clockwork across the vast theatres of interplanetary space. Mars hangs in the void like a rust-coloured sentinel, its thin atmosphere stirring with movements so subtle they register only as the faintest variations in atmospheric pressure and wind velocity. The planet's atmospheric envelope, less than 1% as dense as Earth's, responds to external influences with a sensitivity that would be imperceptible on worlds blessed with thicker gaseous shells. As 3IATLAS approaches its closest passage, the comet's gravitational field begins to interact with Mars's atmospheric dynamics in ways that demonstrate how even the most tenuous planetary atmospheres remain connected to the broader gravitational environment of interplanetary space. The mechanics of atmospheric perturbation operate through principles that bridge the gap between celestial mechanics and fluid dynamics. Mars's atmosphere, composed primarily of carbon dioxide with trace amounts of nitrogen and argon, maintains an average surface pressure of approximately 600 pascals, roughly equivalent to the atmospheric density found 35 kilometers above Earth's surface. This gossamer envelope extends upward through a stratosphere and thermosphere that gradually merge with the vacuum of space, creating boundary conditions where the distinction between atmosphere and interplanetary medium becomes increasingly arbitrary. Gravitational influences propagate through planetary atmospheres as pressure waves that travel at the speed of sound in the local medium. On Mars, where temperatures average -60 degrees Celsius and atmospheric composition differs dramatically from Earth's, sound waves propagate at approximately 240 meters per second, roughly 70% of their velocity in Earth's atmosphere. These acoustic disturbances, generated by the slight gravitational acceleration that 3IATLAS exerts on atmospheric gas molecules, create pressure variations measurable by sensitive barometric instruments but imperceptible to any hypothetical observers standing on the Martian surface. The comet's approach generates what atmospheric physicists call gravitational tides, though these phenomena bear little resemblance to the familiar ocean tides that mark Earth's coastal regions. Instead, they manifest as microscopic variations in atmospheric density that propagate through the gaseous envelope like ripples spreading across a vast three-dimensional pond. These atmospheric tides operate according to the same inverse square law that governs all gravitational interactions, reaching maximum amplitude at the moment of closest approach before diminishing as the comet continues along its trajectory away from Mars. Temperature gradients within Mars's atmosphere create layered density structures that influence how gravitational perturbations propagate through the gaseous medium. The planet's troposphere extends upward approximately 11 kilometers from the surface, maintaining relatively stable temperature and pressure profiles that vary primarily with local topography and seasonal cycles. Above this layer, the stratosphere exhibits temperature inversions created by solar heating of atmospheric constituents, particularly the small amounts of ozone that form through photochemical processes involving carbon dioxide and trace atmospheric components. Atmospheric circulation patterns on Mars follow dynamics fundamentally different from those that drive weather systems on Earth. The planet's rapid rotation period of 24 hours and 37 minutes creates Coriolis effects that deflect moving air masses, but the thin atmosphere and lack of significant water vapor eliminate many of the instabilities that generate terrestrial weather phenomena. Instead, Martian atmospheric dynamics are dominated by temperature-driven convection and the seasonal sublimation and condensation of carbon dioxide at the polar ice caps, processes that create global-scale circulation patterns of remarkable stability and predictability. The gravitational influence of 3IATLAS superimposes tiny perturbations onto these established circulation patterns, creating atmospheric disturbances that propagate according to the fundamental equations of fluid dynamics in a rotating reference frame. These perturbations manifest primarily as variations in wind velocity and direction, changes so small that they fall within the measurement uncertainty of current atmospheric monitoring instruments, yet the physics governing these interactions remains identical to that which drives more dramatic atmospheric phenomena elsewhere in the solar system, scaled down according to the masses and distances involved. Dust suspended in Mars's atmosphere responds to gravitational perturbations in ways that differ subtly from the behavior of gaseous components. Individual dust particles, with masses measured in picograms and diameters of a few micrometers, experience both gravitational acceleration from 3IATLAS and aerodynamic forces from atmospheric motion. The balance between these influences depends on particle size, shape, and density, creating differential responses that could theoretically be detected by instruments sensitive enough to measure microscopic changes in atmospheric opacity or light scattering properties. Seasonal variations in atmospheric pressure create background conditions against which the comet's gravitational influence must be measured. Mars experiences dramatic seasonal cycles as carbon dioxide sublimes from the winter polar cap and condenses at the summer pole, causing global atmospheric pressure to vary by approximately 25% over the course of a Martian year. These large-scale pressure changes dwarf the microscopic perturbations created by 3IATLAS, making direct detection of comet-induced atmospheric effects extremely challenging with current instrumentation capabilities. The planet's weak magnetic field, a remnant of the global magnetosphere that Mars lost billions of years ago, creates local magnetic anomalies that can influence the behavior of charged particles in the upper atmosphere. Though 3IATLAS carries no significant electric charge, its passage through the interplanetary magnetic field embedded in the solar wind creates electromagnetic effects that interact with Mars's magnetized crustal regions in subtle ways. These magnetohydrodynamic phenomena operate on length scales of hundreds of kilometers and timescales of hours, adding another layer of complexity to the already intricate dynamics of comet-planet interaction. Atmospheric escape processes provide another avenue through which 3IATLAS might influence Mars's gaseous envelope, though again at levels below current detection thresholds. The planet continuously loses atmospheric material to space through thermal escape, sputtering by solar wind particles, and other mechanisms that have been depleting its atmosphere for the billions of years. The comet's gravitational field creates infinitesimal variations in the energy distribution of atmospheric particles, potentially altering escape rates by amounts measurable only through extremely sensitive long-term monitoring programs. Computer simulations of atmospheric dynamics during the encounter require coupling gravitational calculations with fluid dynamic models that solve the equations of motion for gaseous media in rotating reference frames. These simulations must account for the spherical geometry of planetary atmospheres, the variable density structure that characterizes different atmospheric layers, and the Coriolis effects created by planetary rotation. The most sophisticated models incorporate detailed thermodynamic properties of carbon dioxide under Martian conditions, along with radiative heating and cooling processes that maintain atmospheric temperature profiles. The encounter demonstrates how gravitational influences propagate through all components of planetary systems, from solid surfaces to gaseous atmospheres to the plasma environments that surround magnetized worlds. Even the most tenuous atmospheric envelopes remain coupled to the gravitational field that pervades interplanetary space, responding to external perturbations according to physical laws that operate with perfect consistency across vastly different scales of space and time. Mars's atmosphere will carry the memory of 3IATLAS's passage in the form of microscopic pressure waves that propagate around the planet at acoustic velocity. Taking approximately 4 hours to complete one circumnavigation, these atmospheric perturbations will gradually dissipate through viscous damping and turbulent mixing, but their initial propagation demonstrates how gravitational interactions couple different components of planetary systems in ways that extend far beyond the simple orbital mechanics that govern the motion of solid bodies through space. Water molecules drift through the vacuum of interplanetary space, invisible witnesses to a story that began when the solar system was young, and planets were still gathering material from the primordial disk of gas and dust that surrounded the nascent sun. Both Mars and 3IATLAS carry within their structures chemical signatures of this ancient epoch, when water existed in forms and locations dramatically different from its current distribution throughout the solar system. The approaching encounter between these two worlds represents a convergence of separate water histories, each preserving isotopic ratios and molecular structures that encode information about conditions that prevailed billions of years before Earth's oceans achieved their familiar blue expanse. The water locked within 3IATLAS, formed under conditions of extreme cold and pressure that characterized the outer regions of the solar nebula during planetary accretion. This ice crystallized at temperatures approaching absolute zero, incorporating trace amounts of heavy water containing deuterium nuclei alongside the more common hydrogen isotopes. The deuterium to hydrogen ratio preserved in cometary ice provides a chemical fingerprint of the interstellar medium from which our solar system condensed, offering direct observational access to the isotopic composition of the molecular cloud that gave birth to our Sun and its family of planets. Spectroscopic analysis of the coma surrounding 3IATLAS reveals water vapor with deuterium concentrations approximately twice those found in Earth's oceans, a difference that speaks to the comet's formation in the outer solar system where heavy isotopes became concentrated through preferential incorporation into ice crystals. This enhanced deuterium signature remains preserved within the comet's nucleus despite billions of years of residence in the Oort cloud, demonstrating the remarkable stability of isotopic ratios over geological timescales when materials remain isolated from chemical alteration processes. Mars preserves its own record of ancient water in the form of hydrated minerals scattered across its surface and trace amounts of water vapor in its tenuous atmosphere. The planet's current atmospheric water content remains vanishingly small, with precipitable water vapor equivalent to a global layer perhaps 10 micrometers thick. Yet geological evidence reveals that Mars once possessed substantial amounts of liquid water, with ancient riverbeds, lake basins, and possible ocean shorelines providing testimony to a warmer, wetter climate that ended more than 3 billion years ago when the planet lost much of its atmosphere to space. The isotopic composition of Martian water differs significantly from both terrestrial and cometary signatures, with deuterium to hydrogen ratios approximately 6 times higher than those found in Earth's oceans. This isotopic enrichment reflects billions of years of preferential loss of lighter hydrogen isotopes to space, as solar radiation and charged particle bombardment gradually stripped away atmospheric water vapor while leaving behind a residual population enriched in heavier isotopes. The current atmospheric water on Mars thus represents a highly evolved remnant of the planet's original water inventory, modified by eons of atmospheric escape processes. Ancient impact craters on both Mars and various asteroids preserve evidence of water delivery during the late heavy bombardment, a period approximately 4 billion years ago, when the inner solar system experienced intense meteorite and comet impacts. These impacts delivered not just rocky material but substantial amounts of water ice, contributing to the early water inventories of terrestrial planets while simultaneously triggering atmospheric loss through impact-induced atmospheric blow-off. The chemical signatures of this ancient water remain detectable in hydrated minerals that formed when liquid water interacted with freshly fractured rock in impact crater environments. Subsurface water ice on Mars exists in vast quantities beneath the planet's polar regions and at various locations in the mid-latitudes where temperature and pressure conditions allow ice to remain stable over geological timescales. Radar observations from orbiting spacecraft reveal ice deposits extending hundreds of meters below the surface, representing water inventories that dwarf the tiny amounts currently present in the atmosphere. This buried ice preserves isotopic signatures that reflect the complex history of water cycling between atmospheric surface and subsurface reservoirs over billions of years of Martian evolution. The water currently escaping from 3IATLAS as vapor in its expanding coma carries isotopic signatures that predate the formation of terrestrial planets, preserving chemical information about the molecular cloud environment that existed before gravitational collapse initiated star formation in our region of the galaxy. Each water molecule sublimating from the comet's nucleus represents a time capsule opened after billions of years of frozen storage, releasing chemical evidence of interstellar conditions that would otherwise remain inaccessible to direct observation. Crystalline structure analysis of cometary ice reveals that water molecules within 3IATLAS exist primarily in amorphous solid phases, created by extremely rapid cooling during the comet's formation. This glassy ice structure differs fundamentally from the crystalline ice familiar in terrestrial environments, maintaining molecular arrangements that preserve information about the temperature and pressure conditions under which the ice originally formed. As solar heating gradually sublimates this ancient ice, it releases not just water vapor but trace amounts of other volatiles that were trapped within the amorphous matrix during the comet's accretion. Clathrate hydrates represent another form of water storage that may exist within both cometary nuclei and Martian subsurface environments. These cage-like crystal structures incorporate guest molecules such as methane, carbon dioxide, or noble gases within frameworks of hydrogen-bonded water molecules, creating stable solid phases that can persist under specific temperature and pressure conditions. The presence of clathrates in cometary nuclei could explain certain observed variations in outgassing rates and volatile compositions as comets approach the inner solar system and these exotic ice phases begin to destabilize. Laboratory experiments studying the behavior of water ice under simulated space conditions reveal complex phase transitions and chemical evolution processes that occur over timescales ranging from seconds to millions of years. Cosmic ray bombardment, ultraviolet radiation, and thermal cycling create chemical reactions within ice matrices that produce organic compounds, modify isotopic ratios, and alter crystal structures in ways that depend sensitively on the detailed environmental conditions experienced over extended periods. These experimental results help interpret the chemical signatures observed in both cometary and Martian water reservoirs. The encounter between Mars and 3IATLAS creates an opportunity for comparative analysis of water inventories that formed under vastly different conditions and evolved through completely separate pathways over the past 4.5 billion years. Though no direct exchange of material will occur during their distant gravitational interaction, the juxtaposition of these two water-bearing objects allows scientists to study how the same fundamental molecule can preserve different types of chemical information depending on the environmental history it experiences. Theoretical models of early solar system evolution suggest that comets delivered substantial fractions of the water currently found on terrestrial planets, though the isotopic mismatches between cometary and terrestrial water indicate that multiple sources contributed to planetary water inventories. The approaching encounter provides a natural experiment for studying how water-bearing objects interact gravitationally while preserving their distinct chemical signatures, demonstrating the physical processes that operated during the chaotic early epochs when planetary water inventories were still being established through bombardment by asteroids and comets. Each molecule of water vapor escaping from 3IATLAS carries within its isotopic structure a message from the interstellar medium that gave birth to our solar system. While the trace water vapor in Mars's atmosphere preserves isotopic evidence of billions of years of atmospheric evolution on a world that once harbored rivers, lakes, and possibly oceans. Behind 3IATLAS, stretching across millions of kilometers of interplanetary space, flows a river of dust so tenuous that its individual particles drift separated by distances measured in cubic kilometers of near-perfect vacuum. These microscopic grains represent the physical substance of the comet itself, liberated from their icy matrix by solar heating and carried away from the nucleus on streams of sublimating gas. Each particle carries within its crystalline structure a record of conditions that prevailed during the solar system's formation, preserving mineral compositions and isotopic signatures that encode information about stellar nucleosynthesis, supernova explosions, and the chemical evolution of the interstellar medium from which our Sun and planets condensed. The dust trail forms through processes that operate with mechanical precision, governed by the same physical laws that determine planetary orbits and stellar evolution. As solar radiation heats the comet's surface, subsurface ice sublimes directly from solid to gas, creating pressure that drives jets of material away from the nucleus at velocities measured in hundreds of meters per second. These gas jets carry with them embedded dust particles that range in size from submicron grains, smaller than bacteria, to boulder-sized chunks weighing several kilograms. The size distribution follows power law relationships that reflect the fractal nature of cometary nuclei, with smaller particles vastly outnumbering larger ones according to mathematical patterns that appear throughout nature. Radiation pressure from sunlight acts upon these escaping dust grains with forces that depend on their size, composition, and distance from the Sun. Particles smaller than approximately 1 micrometer in diameter experience radiation pressure, forces that exceed solar gravitational attraction, accelerating them outward from the solar system at speeds that carry them beyond planetary orbits within years or decades. Larger particles feel weaker radiation pressure relative to their mass, allowing solar gravity to retain them in bound orbits that will carry them around the Sun for millions of years after their parent comet has departed the inner solar system. The orbital dynamics of dust particle evolution create a complex three-dimensional structure that extends far beyond the visible boundaries of the comet's coma and tail. Each particle follows its own independent orbit around the Sun, with orbital elements determined by the velocity and direction of its ejection from the parent nucleus. Particles ejected when the comet was closer to the Sun follow orbits with smaller semi-major axes and shorter periods than those released during the comet's more distant phases, creating a dispersed stream of material that gradually spreads throughout the inner solar system. Poynting-Robertson drag provides another mechanism that shapes the long-term evolution of cometary dust streams. This relativistic effect arises from the finite speed of light, causing dust particles to experience a systematic orbital decay as they absorb and re-emit solar radiation. The absorbed photons carry momentum in the direction of the particle's orbital motion, while the re-emitted thermal radiation carries momentum in random directions, creating a net drag force that gradually spirals particles inward toward the Sun. This process operates over timescales of thousands to millions of years, depending on particle size and orbital characteristics. The dust stream from 3IATLAS will persist long after the comet itself has retreated beyond the orbit of Neptune, creating a permanent addition to the population of interplanetary dust that permeates the solar system. This dust contributes to the zodiacal light visible from Earth, as a faint glow extending along the ecliptic plane before dawn and after sunset. Sunlight scattered by microscopic particles distributed throughout the inner solar system. The total mass of interplanetary dust equals approximately the mass of a modest asteroid. Yet this material remains distributed across volumes measured in cubic astronomical units. Laboratory analysis of cometary dust particles collected by spacecraft missions reveals mineral compositions that preserve records of high-temperature processes that occurred in the early solar nebula. These findings challenge simple models of comet formation that assumed all cometary material condensed in the cold outer regions of the disk. Instead, Dust grains show evidence of thermal processing at temperatures exceeding 1000 Kelvin, suggesting that material formed near the young sun was transported outward and incorporated into cometary nuclei through large-scale mixing processes that operated during planetary accretion. The crystalline structure of silicate minerals within cometary dust provides information about the cooling rates and chemical environments that characterize different regions of the solar nebula during planetary formation. Olivine and pyroxene crystals preserve evidence of rapid cooling from molten states, while hydrated minerals indicate subsequent alteration by liquid water in asteroidal parent bodies that were later disrupted and incorporated into cometary nuclei. This mineralogical diversity demonstrates the complex history of solid materials that were recycled through multiple environments before achieving their current incorporation in cometary ice. Organic compounds detected in cometary dust samples include complex carbon-bearing molecules that may represent some of the most primitive organic matter in the solar system. These compounds formed through irradiation processing of simpler molecules in the interstellar medium or during the earliest phases of solar nebula evolution, preserving chemical structures that predate the origin of life on Earth. The delivery of such organic compounds to terrestrial planets through cometary bombardment may have contributed essential building blocks for the biochemical processes that eventually led to the emergence of biological systems. The size-velocity relationship observed in cometary dust streams follows patterns that reflect the physics of gas-dust interaction during the particle ejection from the nucleus. Smaller particles couple more efficiently to the expanding gas flow, achieving higher ejection velocities that carry them farther from the comet before solar radiation pressure takes over. Larger particles decouple from the gas flow closer to the nucleus, following trajectories that remain more closely aligned with the comet's orbital motion. This differential velocity distribution creates dust streams with complex spatial structures that evolve over time as particles disperse according to their individual orbital elements. Gravitational perturbations from planets gradually modify the orbits of dust particles in the stream, creating resonant structures and gaps that mirror the architecture observed in planetary ring systems and asteroid belts. Particles with orbital periods that form simple ratios with planetary orbital periods experience systematic gravitational perturbations that can either stabilize their orbits or drive them into chaotic trajectories leading to collision with planets or ejection from the solar system. These gravitational resonances create long-term structure in dust streams that persists for millions of years after the parent comet's passage. Magnetic fields embedded in the solar wind interact with electrically charged dust particles to create electromagnetic forces that supplement the gravitational and radiative forces shaping particle trajectories. Cosmic ray bombardment and photoelectric emission from solar ultraviolet radiation maintain net electric charges on dust grains that vary with their composition, size, and local plasma environment. These electromagnetic effects remain small compared to gravitational and radiative forces for most particle sizes, but they illustrate the variety of physical processes that influence the evolution of cometary debris over extended periods. The dust trail from 3IATLAS will eventually intersect Earth's orbit at predictable times and locations determined by the orbital mechanics of both the particles and our planet. When Earth passes through this debris stream, the particles will enter our atmosphere as meteors, creating brief flashes of light as they vaporize due to atmospheric friction. These meteor showers will provide future opportunities for direct sampling of cometary material, allowing detailed laboratory analysis of dust grains that preserve chemical and isotopic signatures of the early solar system. The gradual dispersal of cometary dust throughout interplanetary space demonstrates how individual objects contribute to the background population of solid particles that fills the volume between planets. Over billions of years, countless comets have contributed similar dust streams, creating the current inventory of interplanetary debris that interacts with planetary atmospheres, influences spacecraft operations, and provides raw material for the continued accretion of solid matter onto planetary surfaces throughout the solar system. The solar wind streams outward from the Sun's corona at velocities exceeding 400 kilometers per second, carrying with it a magnetic field frozen into the plasma according to principles of magneto-hydrodynamics that govern the behavior of ionized gases throughout the universe. This continuous outflow of charged particles represents the Sun's atmosphere expanding into interplanetary space, creating a dynamic environment where electromagnetic forces interact with gravitational influences to shape the trajectories and physical properties of objects moving through the inner solar system. As 3IATLAS approaches its encounter with Mars, both the comet's expanding coma and the planet's thin atmosphere become immersed in this flowing plasma, creating electromagnetic interactions that demonstrate how charged particle dynamics operate on scales from planetary magnetospheres to galactic magnetic fields. The comet's nucleus, composed primarily of water ice mixed with rocky debris and organic compounds, begins to develop an electrically charged surface as solar ultraviolet radiation strips electrons from atoms and molecules exposed to the vacuum of space. This photoelectric effect creates a complex electrical environment around the nucleus, with different regions maintaining positive or negative charges depending on their composition, temperature, and exposure to solar radiation. The resulting electric fields accelerate ions and electrons in the expanding coma, creating electrical currents that interact with the magnetic field embedded in the solar wind to produce forces that can influence the motion of charged particles escaping from the comet. Mars possesses no global magnetic field comparable to Earth's magnetosphere, having lost its planet-wide magnetic dynamo billions of years ago when its core began to cool and solidify. However, remnant magnetization preserved in ancient crustal rocks creates a patchwork of localized magnetic anomalies that interact with the solar wind in complex ways. These magnetic field lines, oriented in random directions determined by the geological processes that formed the crustal rocks, create magnetic barriers that partially deflect solar wind particles while allowing others to penetrate directly to the planet's upper atmosphere. The interaction between solar wind and cometary coma creates one of the most visually spectacular phenomena in the solar system: the formation of cometary tails that point away from the Sun, regardless of the comet's direction of motion. This tail formation results from radiation pressure acting on dust particles and electromagnetic forces acting on ionized gas molecules in the coma. The ion tail, composed of charged particles streaming away from the nucleus at velocities reaching hundreds of kilometers per second, follows magnetic field lines embedded in the solar wind like a cosmic windsock, indicating the direction of plasma flow in interplanetary space. Magnetic reconnection events occur when oppositely directed magnetic field lines in the solar wind encounter the comet's induced magnetosphere, creating temporary connections that allow rapid energy transfer between different regions of the plasma environment. These reconnection events can accelerate charged particles to high energies while creating fluctuations in the local magnetic field strength that propagate outward from the comet as magneto-hydrodynamic waves. The energy released during magnetic reconnection demonstrates the same physical processes that drive solar flares, auroras on the magnetized planets, and energy release in stellar coronae throughout the galaxy. The solar wind's magnetic field strength varies with the distance from the Sun, according to relationships that reflect the conservation of magnetic flux, as the plasma expands into the increasing volume of interplanetary space. At Mars's orbital distance, the interplanetary magnetic field maintains an average strength of approximately 5 nanotesla, roughly 10,000 times weaker than Earth's surface magnetic field, yet sufficient to influence the behavior of charged particles over the vast scales of interplanetary space. This weak but persistent magnetic field provides the medium through which electromagnetic disturbances propagate from the Sun to the outer reaches of the solar system. Plasma instabilities develop in the region where solar wind encounters the comet's coma, creating turbulent mixing that accelerates charged particles while generating electromagnetic radiation across a broad spectrum of frequencies. These plasma physics phenomena operate according to principles that govern fusion reactions in stellar cores, particle acceleration in supernova shock waves, and energy transport in the magnetic environment surrounding black holes. The comet's interaction with solar wind thus provides a natural laboratory for studying fundamental plasma processes that operate throughout the universe. The velocity of solar wind particles creates a bow shock wave in the plasma upstream from obstacles that deflect or absorb the flowing charged particles. Though neither Mars nor 3IATLAS possesses sufficient mass or magnetic field strength to create dramatic bow shocks comparable to those observed around magnetized planets, both objects generate subtle disturbances in the solar wind flow that propagate upstream at the local Alfvén wave velocity. These disturbances carry information about the obstacle's properties across interplanetary distances, allowing electromagnetic signals to travel faster than the bulk plasma flow. Charge exchange processes occur when solar wind protons encounter neutral atoms in cometary coma or planetary exospheres, creating energetic neutral atoms that escape local electromagnetic influences while producing ions that become incorporated into the solar wind flow. These charge transfer reactions demonstrate how electromagnetic and gravitational environments remain coupled through atomic physics processes that operate on microscopic scales, yet influence macroscopic plasma dynamics across planetary and cometary systems. The electrical conductivity of ionized gas in the comet's coma creates conditions where magnetic field lines become frozen into the plasma, moving with the bulk flow of charged particles as they stream away from the nucleus. This coupling between magnetic fields and plasma motion ensures that the comet's induced magnetosphere maintains a complex, time-varying structure that depends on variations in solar wind properties, the comet's outgassing rate, and the orientation of the interplanetary magnetic field. The resulting magnetic field configuration resembles a twisted ribbon extending millions of kilometers downstream from the nucleus. High-energy cosmic ray particles, originating from supernova explosions and other violent astrophysical processes throughout the galaxy, continuously bombard both Mars and 3IATLAS with charged particles carrying energies millions of times greater than typical solar wind particles. These cosmic rays create secondary radiation when they interact with planetary atmospheres or cometary nuclei, generating cascades of subatomic particles that can penetrate deep into solid matter while creating isotopic modifications that accumulate over geological timescales. The heliospheric current sheet, a vast spiral structure created by the Sun's rotating magnetic field, extends throughout the solar system as a boundary between regions of oppositely directed magnetic field lines. When Mars or 3IATLAS crosses this current sheet, they experience abrupt changes in magnetic field direction and solar wind properties that can influence atmospheric escape rates, particle acceleration process, and the formation of cometary tail structures. These current sheet crossings occur at intervals determined by the Sun's 27-day rotation period and the object's orbital velocities. Electromagnetic wave propagation through the solar wind plasma creates a complex environment where radio waves, plasma waves, and magnetic field fluctuations interact according to the dispersion relations that characterize different wave modes in magnetized plasmas. These waves can accelerate charged particles, heat plasma to temperatures exceeding those in the solar corona, and transport energy across vast distances through processes that operate in environments ranging from laboratory fusion experiments to the magnetospheres of distant planets orbiting other stars. The encounter between Mars and 3IATLAS occurs within this dynamic electromagnetic environment where solar-wind interactions create coupling between gravitational and electromagnetic forces across multiple spatial and temporal scales. The charged particle population surrounding both objects will experience subtle modifications during their gravitational encounter, demonstrating how celestial mechanics operates within the broader context of plasma physics that characterizes most of the visible matter in the universe. Deep within the theoretical frameworks that describe celestial motion, the orbital period of 3IATLAS carries encoded information about its origin that extends far beyond the gravitational architecture of our current solar system. Astronomers calculating the comet's orbital elements discover characteristics that suggest this visitor arrived not from the familiar Oort cloud that surrounds our Sun, but from the even more distant realm of interstellar space itself. The mathematical signatures embedded in its trajectory speak to gravitational encounters with stellar systems that may have occurred millions of years ago, when our Sun occupied a different position within the slowly rotating spiral arms of the Milky Way galaxy. The concept of orbital energy provides the key to understanding how 3IATLAS acquired its current trajectory through space. Objects gravitationally bound to the Sun possess negative total energy, with their kinetic energy always less than the gravitational potential energy required to escape the solar system entirely. Comets from the Oort cloud exhibit orbital energies that place them just barely within the Sun's gravitational influence, moving so slowly at aphelion that minor perturbations from passing stars can easily alter their orbits. Yet 3IATLAS displays orbital characteristics that suggest positive total energy, indicating that it approaches our solar system from the direction of the constellation Lynx with a velocity component that exceeds the local escape velocity. The mathematics of hyperbolic orbits describe trajectories followed by objects with sufficient energy to escape gravitational capture, creating paths through space that approach their parent star along one branch of a hyperbola before receding along the opposite branch toward infinity. Unlike the elliptical orbits that characterize planets and most comets, hyperbolic trajectories never close upon themselves, representing one-time encounters between objects that originated in separate gravitational environments. The precise shape of a hyperbolic orbit depends on the object's velocity at infinity, a theoretical construct that describes the speed an object would maintain if it could travel infinitely far from all gravitational influences. Stellar kinematics within our local galactic neighborhood provide the context necessary to understand how 3IATLAS might have acquired its remarkable trajectory. Our Sun moves through space at approximately 20 kilometers per second relative to the local standard of rest, a reference frame defined by the average motion of nearby stars within our spiral arm. This stellar motion carries the entire solar system through a constantly changing stellar environment, with different stars passing within gravitational influence over timescales of millions of years. During these encounters, cometary objects in the outer reaches of stellar systems can be exchanged between different gravitational domains through processes that operate according to the same three-body dynamics that govern planetary satellite systems. The Alpha Centauri system, our nearest stellar neighbour at a distance of 4.37 light-years, exemplifies the type of gravitational environment that could contribute interstellar comets to our solar system. This triple star system consists of two sun-like stars orbiting each other every 80 years, accompanied by a more distant red dwarf companion that completes its orbit over periods measured in hundreds of thousands of years. Gravitational perturbations within such complex stellar systems can occasionally accelerate cometary objects to velocities sufficient for interstellar travel, though the precise mechanisms remain subjects of ongoing theoretical investigation. Computer simulations of galactic dynamics reveal that stellar encounters capable of exchanging cometary material occur perhaps once every few million years for typical stellar systems. These encounters need not involve close approaches between stellar cores. Gravitational influences can extend across several light years when dealing with objects in the distant reaches of stellar Oort clouds. The cumulative effects of multiple weak encounters, combined with occasional stronger perturbations from closer stellar passages, create a gradual mixing of cometary populations throughout local stellar neighborhoods over timescales comparable to galactic rotation periods. The discovery of interstellar objects within our solar system represents a relatively recent development in observational astronomy, made possible by automated sky surveys capable of detecting faint, rapidly moving objects against the stellar background. Oumuamua, discovered in 2017, provided the first confirmed example of an interstellar visitor, displaying orbital characteristics and physical properties that clearly distinguished it from solar system natives. The subsequent identification of additional interstellar candidates, including 3IATLAS, suggests that such objects may pass through our solar system regularly, most remaining undetected due to their small size and brief visibility during solar system passage. Theoretical models of interstellar object populations predict that several interstellar comets or asteroids should pass within the orbit of Jupiter each year, though most remain too faint for detection by current observational capabilities. These predictions depend on assumptions about the efficiency of stellar encounters in ejecting material from planetary systems, the survival rates of small objects during interstellar travel, and the density of such objects in local interstellar space. Improved sky surveys and detection algorithms continue to refine these estimates while discovering additional examples of interstellar visitors. The chemical composition of interstellar objects provides potential insights into planetary formation processes in stellar systems with different metallicities, ages, and dynamical histories than our own. Spectroscopic analysis of 3IATLAS during its passage through the inner solar system may reveal isotopic ratios and molecular abundances that reflect nucleosynthetic processes in stars with different masses and evolutionary histories. Such measurements would provide direct observational access to material that formed under physical and chemical conditions potentially very different from those that characterized our solar nebula 4.5 billion years ago. Gravitational mechanics dictate that interstellar objects entering our solar system will have their trajectories modified by encounters with planets, potentially transforming some visitors from hyperbolic to elliptical orbits that result in permanent capture. Jupiter, with its enormous mass and strategic position in the outer solar system, serves as the most likely agent for such orbital modifications. Objects that pass sufficiently close to Jupiter can lose enough kinetic energy to become gravitationally bound to the Sun, joining the permanent population of solar system bodies despite their exotic origins. The long-term stability of captured interstellar objects depends on complex interactions with multiple planets over extended periods, creating chaotic dynamics that make detailed predictions impossible beyond certain time horizons. Some captured objects may remain in stable orbits for millions of years, before subsequent planetary encounters eject them back to interstellar space, while others might evolve into asteroid-like orbits that persist for the remaining lifetime of the solar system. These evolutionary pathways demonstrate how gravitational systems maintain dynamic equilibrium through continuous exchange of material with their surroundings. Astrobiological implications of interstellar objects include the possibility that they could transport organic compounds or even dormant biological material between stellar systems, potentially contributing to the distribution of life throughout the galaxy. Though the survival of complex organic molecules during millions of years of interstellar travel remains highly uncertain, laboratory experiments suggest that some biochemical components might persist under the extreme conditions of interstellar space when protected within the interior of solid objects. The trajectory of 3IATLAS through our solar system represents a brief intersection between our local gravitational environment and the broader galactic context within which all stellar systems evolve. Its hyperbolic orbit carries encoded information about stellar encounters that occurred when our Sun occupied different positions within the galaxy's spiral structure, demonstrating how astronomical objects serve as messengers carrying information across vast distances and timescales about the physical processes that shape cosmic evolution on scales from planetary systems to galactic structure. Mars rotates beneath a star-filled sky with the steady rhythm that has marked planetary days and nights for billions of years. Its ancient surface scarred by the impact craters that serve as silent witnesses to the violent bombardment that characterized the early solar system. The planet's geological memory extends back through eons of cosmic history, preserving in its rocks and minerals a detailed record of environmental changes that transformed a world that once harbored flowing rivers and possible oceans into the cold, dry landscape that confronts 3IATLAS during their gravitational encounter. These crater-marked plains and valley networks maintain their patient vigil as the ancient comet approaches, adding its own subtle gravitational signature to the countless influences that have shaped Martian geology across deep time. The largest impact basins on Mars formed during the late heavy bombardment approximately 4 billion years ago, when the inner solar system experienced intense asteroid and comet impacts as the giant planets achieved their current orbital configuration. Hellas Basin stretches across 2,300 kilometers of the southern hemisphere, its rim walls rising several kilometers above the surrounding terrain while its floor extends 9 kilometers below the mean elevation datum. This enormous scar represents one of the largest impact structures in the solar system, formed when an asteroid perhaps 150 kilometers in diameter struck Mars with kinetic energy equivalent to millions of nuclear weapons. The physics of hypervelocity impacts creates geological structures that preserve information about both the impacting object and the target materials present at the time of collision. When cosmic projectiles strike planetary surfaces at velocities measured in tens of kilometers per second, the resulting shock waves generate pressures and temperatures that rival those found in stellar interiors, creating exotic mineral phases that exist nowhere else in nature. These shock metamorphic minerals provide forensic evidence for ancient impact events, allowing planetary geologists to reconstruct the sizes, velocities, and compositions of objects that collided with Mars billions of years ago. Crater counting techniques reveal the relative ages of different Martian terrains by analyzing the density and size distribution of impact scars accumulated over geological time. Heavily cratered regions in the southern highlands preserve surfaces that date back to Mars's earliest epoch, when the planet's atmosphere was thicker and liquid water could persist on the surface for extended periods. Younger volcanic plains in the northern lowlands display fewer craters per unit area, indicating more recent resurfacing by lava flows that buried older impact structures beneath layers of solidified magma. The morphology of Martian impact craters reflects the environmental conditions that prevailed when each impact occurred, particularly the presence or absence of subsurface ice and atmospheric density variations that influenced crater formation processes. Fresh craters display sharp rim crests and well-preserved ejecta blankets that radiate outward from the impact site like frozen explosions captured in stone. Older craters show evidence of erosional modification by wind, occasional water flow, and gradual relaxation of topographic relief through geological processes that operate over millions of years. Atmospheric interactions during the crater formation process create unique morphological features that distinguish Martian impact structures from those found on airless bodies like the Moon. The planet's thin atmosphere provides sufficient resistance to modify the ballistic trajectories of ejecta blocks, creating asymmetric debris patterns that reflect wind conditions at the time of impact. Some craters display evidence of atmospheric blast effects, with ejecta deposits that show signs of interaction with shock waves propagating through the gaseous medium surrounding the impact site. The transition between heavily cratered terrain and smoother volcanic plains marks one of the most significant geological boundaries on Mars, representing a fundamental change in the planet's geological activity that occurred approximately 3.5 billion years ago. This transition coincides with the end of the heavy bombardment period and the beginning of the Mars' current geological era, characterized by localized volcanic activity, gradual atmospheric loss, and the cessation of global-scale hydrological processes that once modified the planet's surface. Rampart craters represent a distinctive class of Martian impact structures that formed when projectiles struck ice-rich subsurface materials, creating fluid ejecta flows that spread across the surrounding terrain like frozen mudslides. These lobate ejecta deposits indicate the presence of ground ice at the time of impact, providing evidence for climate conditions that allowed ice to accumulate and persist in Martian soils. The distribution of rampart craters across the planet's surface reveals how subsurface ice abundance has varied with latitude and geological time. Valley networks carved into the ancient cratered terrain preserve evidence of surface water flow during Mars' earliest geological epoch, when impact-generated hydrothermal systems may have created local environments warm enough to support liquid water despite globally cold conditions. These branching channel systems display morphological characteristics similar to terrestrial river networks, including tributary junctions, meander patterns, and sedimentary deposits that accumulated in ancient lake basins downstream from highland watersheds. The preservation of these ancient geological features demonstrates Mars's geological quiescence compared to more geologically active worlds like Earth, where plate tectonics and vigorous erosion rapidly erase evidence of ancient surface processes. Mars lacks plate tectonics, allowing its oldest terrains to persist largely unchanged for billions of years, while accumulating detailed records of environmental conditions that prevailed during the planet's earliest history. This geological stability makes Mars an invaluable archive for studying planetary processes that operated during the first billion years of solar system evolution. Seasonal frost deposits currently accumulate and sublime in polar regions and at high latitudes where temperature and pressure conditions allow carbon dioxide and water ice to remain stable on the surface. These modern ice deposits demonstrate how Mars continues to experience active geological processes, though at rates far slower than those that operated during the planet's early history. The seasonal cycle of frost deposition and sublimation creates pressure variations in the thin atmosphere that drive weak wind systems capable of transporting dust across continental distances. Dust devil activity represents another ongoing geological process that continues to modify Martian surface features, creating dark tracks visible in orbital imagery as these miniature tornadoes sweep across the landscape. These atmospheric vortices form when solar heating creates convective instabilities in the near-surface atmosphere, generating rotating columns of air that can reach heights of several kilometers while maintaining diameters of tens of meters. Though individually insignificant, the cumulative effects of thousands of dust devils over millions of years contribute measurable amounts of erosion and sediment transport. The gravitational influence of 3IATLAS will add its own infinitesimal contribution to the forces that continue to shape Mars' geological evolution, creating tidal stresses within the planet's crust that remain far too small to trigger any detectable geological activity. Yet these same tidal forces demonstrate how these gravitational interactions between celestial bodies operate across all scales, from the Earth-Moon system that drives ocean tides to the galactic tidal forces that influence stellar orbits within spiral arms. Ancient impact craters scattered across Mars' surface serve as passive observers of this latest gravitational encounter, their rim walls and central peaks providing elevated vantage points from which to witness the cosmic choreography unfolding overhead. These geological monuments to cosmic violence will continue their patient watch long after 3IATLAS has departed for the outer solar system, carrying forward into the future their detailed records of planetary evolution across the deep time scales that characterize geological processes throughout the cosmos. Beyond the orbit of Jupiter, 3IATLAS carries with it a momentum vector that points toward the constellation Draco, tracing a hyperbolic arc through space that will carry this ancient wanderer far from the gravitational embrace of our Sun and back into the cold depths of interstellar space. The comet's trajectory, now permanently altered by its gravitational encounter with Mars, follows mathematical relationships that ensure its eventual escape from the solar system with a velocity sufficient to traverse the distance between stars over periods measured in millions of years. This outbound journey represents the final chapter of the comet's brief visit to our planetary neighborhood. A cosmic story that began when gravitational perturbations first set it on a collision course with the inner solar system eons ago. The physics of escape velocity governs how objects achieve permanent departure from gravitational systems, requiring speeds that exceed the square root of twice the gravitational parameter divided by the distance from the central mass. For objects departing from Mars' orbital distance, this critical velocity equals approximately 24 kilometers per second relative to the Sun, though the actual escape process involves complex three-dimensional trajectories that must account for planetary perturbations and the non-uniform gravitational environment of a multi-body system. 3IATLAS now carries kinetic energy sufficient to overcome solar gravitational attraction permanently, ensuring its continued motion toward interstellar space regardless of any future planetary encounters. The comet's velocity at infinity, a theoretical construct representing its speed after escaping all solar gravitational influence, has been modified by approximately 300 meters per second as a result of its close passage by Mars. This change, seemingly insignificant when compared to the comet's total velocity of several dozen kilometers per second, will alter its arrival time at the heliopause by thousands of years and shift its ultimate destination among the stars by distances measured in light years. Such sensitivity to small perturbations demonstrates the chaotic nature of gravitational dynamics over astronomical timescales, where tiny changes in initial conditions produce dramatically different long-term outcomes. As 3IATLAS recedes from the inner solar system, its coma and tail structures will gradually diminish as decreasing solar radiation reduces the sublimation rate of surface volatiles. The comet's nucleus, originally perhaps 5 kilometers in diameter, has lost several meters of surface material during its passage through the region where solar heating drives active outgassing. This mass loss, totaling perhaps millions of tons of ice and dust, represents only a small fraction of the comet's total mass, yet demonstrates how solar encounters gradually erode these ancient objects over multiple passages through stellar systems. The dust trail deposited during the comet's active phase will persist in the inner solar system for millions of years, creating a permanent monument to 3IATLAS's brief visit. This debris stream will eventually spread throughout the inner solar system as gravitational perturbations from planets gradually disperse the particles along orbits with slightly different periods and inclinations. Future encounters between Earth and this debris stream will create meteor showers that provide direct samples of interstellar material for laboratory analysis, offering rare opportunities to study matter that originated beyond our solar system. Solar wind pressure and the declining strength of solar radiation will eventually bring the comet's active phase to a complete end as it crosses the orbit of Neptune and continues toward the heliopause. At these vast distances, surface temperatures will drop below the sublimation point of even the most volatile compounds, returning the nucleus to the dormant state that characterized its existence during millions of years of interstellar travel. The comet will become essentially invisible to telescopic observation, detectable only through gravitational effects or direct imaging, if it happens to occult background stars during its outward journey. The heliopause, marking the boundary where solar wind pressure balances the interstellar medium, currently lies approximately 120 astronomical units from the Sun in the direction of the comet's departure. This boundary represents not a physical barrier but a transition zone where the charged particle environment changes from solar wind-dominated to interstellar, medium-dominated conditions. 3IATLAS will cross this boundary, carrying with it chemical and isotopic signatures that encode information about our solar system's composition, potentially delivering this information to other stellar systems over cosmic timescales. Interstellar space presents environmental conditions far more hostile than those encountered within stellar systems, with cosmic ray intensities orders of magnitude higher than those experienced near planets and their protective magnetospheres. These high-energy particles will gradually modify the surface composition of the comet's nucleus through nuclear reactions that create exotic isotopes and complex organic molecules. Over millions of years of interstellar travel, cosmic ray bombardment will penetrate several meters into the nucleus interior, creating chemical gradients that reflect the duration and intensity of exposure to galactic radiation, the local interstellar cloud, through which our solar system currently moves, maintains a density of approximately 1,000 atoms per cubic meter and a temperature of several thousand Kelvin. Though this environment registers as perfect vacuum by terrestrial standards, it provides sufficient material density to create drag forces that will gradually slow the comet's motion over millions of years of interstellar flight. This interstellar medium also contains magnetic fields and cosmic ray populations that differ from those within the heliosphere, creating new physical environments that will influence the comet's surface properties and internal structure. Stellar encounters during the comet's interstellar journey will periodically alter its trajectory through gravitational perturbations that operate according to the same principles that governed its interactions within our solar system. The nearest star in the direction of the comet's motion lies approximately 20 light-years away, requiring roughly 4 million years for 3IATLAS to complete the journey at its current velocity. During this transit, the comet may pass through the gravitational influence of other stellar systems, potentially experiencing capture events that could incorporate it into alien planetary systems as a permanent residence. The probability of eventual capture by another stellar system depends on the precise trajectory that 3IATLAS follows through local stellar neighborhoods and the orbital characteristics of stars it encounters during its interstellar voyage. Computer simulations suggest that most objects ejected from stellar systems continue wandering through interstellar space indefinitely, occasionally passing through other systems without achieving gravitational capture. However, close encounters with multiple star systems over millions of years create cumulative probabilities for capture that may eventually exceed 50% for some trajectories. Information encoding within the comet's physical and chemical structure will provide any future observers with indirect evidence about conditions that prevailed in our solar system during the early 21st century. Isotopic ratios preserved in the nucleus ice will carry signatures of solar wind composition, cosmic ray exposure histories, and thermal processing during passage through the inner solar system. These chemical fingerprints represent a form of natural space archaeology, preserving information about stellar environments across galactic timescales. The comet's departure from our solar system marks the conclusion of a gravitational story that began when unknown perturbations first set it on its current trajectory millions of years ago. Yet this departure also represents the beginning of a new chapter in cosmic evolution. As 3IATLAS carries materials and information from our solar system toward encounters with stellar environments that may operate according to very different physical and chemical principles, the mathematical inevitability of its escape demonstrates how gravitational mechanics operates with perfect consistency across scales, from planetary encounters to galactic dynamics, connecting local astronomical events to the broader cosmic processes that drive stellar and galactic evolution. The ancient wanderer continues its patient journey toward the stars, carrying within its frozen matrix a chemical record of our solar system that will persist long after our sun has evolved beyond its current state, serving as an eternal messenger travelling between the stars with news of worlds that orbit a modest yellow star in one spiral arm of an ordinary galaxy among billions scattered throughout the observable universe. Within the sophisticated tracking stations scattered across Earth's surface and orbiting above its atmosphere, sensitive instruments record the subtle gravitational echoes that ripple through the solar system as 3IATLAS completes its closest approach to Mars. These measurements require precision that pushes current technology to its fundamental limits, detecting changes in planetary motion equivalent to the gravitational influence of a butterfly landing on a mountain yet accumulated over time, scales that span months of careful observation, the data streams flowing from radio telescopes, laser interferometers, and atomic clocks reveal how even the most distant gravitational encounters leave permanent imprints on the orbital mechanics that govern planetary motion throughout the solar system. The concept of gravitational memory emerges from general relativity theory, which describes gravity not as a force but as the curvature of space-time around massive objects. When 3IATLAS passes through the gravitational field generated by Mars, it creates ripples in the fabric of space-time itself that propagate outward at the speed of light, carrying information about the encounter to every corner of the solar system. These gravitational waves remain far too weak for direct detection by current instruments, yet their theoretical existence demonstrates how local gravitational events influence the global structure of space-time throughout extended regions surrounding stellar systems. Mars experiences the most significant orbital modifications from its encounter with the comet, though these changes manifest as alterations in velocity measured in millimeters per second and positional shifts accumulated over decades of subsequent orbital motion. The planet's orbital period around the Sun, currently 687.09 Earth days, will change by perhaps a few seconds due to the gravitational interaction with 3IATLAS. This seemingly negligible modification will cause Mars to arrive at specific points in its orbit minutes earlier or later than predictions based on pre-encounter orbital elements, creating discrepancies that accumulate over multiple orbital revolutions. The mathematical framework of celestial mechanics describes these orbital modifications through perturbation theory, which treats gravitational encounters as temporary departures from the perfect elliptical motion described by Kepler's laws. Each planetary orbit can be characterized by 6 orbital elements that completely specify its three-dimensional trajectory through space: semi-major axis, eccentricity, inclination, longitude of ascending node, argument of perihelion, and mean anomaly at a reference epoch. The encounter with 3IATLAS modifies each of these elements by amounts that depend on the masses involved, the minimum separation distance, and the relative velocities during closest approach. Laser-ranging experiments that bounce coherent light pulses off retroreflectors placed on spacecraft orbiting Mars provide the precision necessary to detect these orbital modifications through direct measurement. The round-trip travel time for laser pulses traveling between Earth and Mars varies with the distance between planets, allowing astronomers to determine interplanetary distances with accuracy measured in centimeters across hundreds of millions of kilometers of space. Changes in Mars' orbital velocity equivalent to a leisurely walking pace become detectable through accumulated timing differences that build up over months of continuous observation. The gravitational influence of 3IATLAS also creates subtle perturbations in the orbits of Mars' 2 small moons, Phobos and Deimos, which respond more dramatically to external gravitational fields due to their lower masses and closer proximity to the encounter. These tiny satellites, probably captured asteroids with masses measured in billions of tons, rather than the planetary scales that characterize their parent world, experience orbital modifications that exceed those affecting Mars itself by factors proportional to their mass ratios. The resulting changes in their orbital periods and orientations provide additional observational signatures that confirm theoretical predictions of the encounter's gravitational effects. Spacecraft currently in orbit around Mars serve as additional gravitational sensors, their trajectories modified by the same perturbations that affect the planet's natural satellites. The Mars Reconnaissance Orbiter, Mars Odyssey, and other robotic explorers maintain orbital altitudes where they remain sensitive to changes in the planet's gravitational field caused by mass redistribution, atmospheric variations, and external gravitational influences. Navigation teams monitoring these spacecraft detect anomalous trajectory changes that require correction maneuvers, providing independent confirmation of theoretical predictions for how the comet encounter affects the Martian gravitational environment. The precision required for these measurements challenges the fundamental limits imposed by quantum mechanics, general relativity, and thermodynamic noise in detection systems. Atomic clocks used for spacecraft navigation achieve stability equivalent to losing less than 1 second over the age of the universe. Yet even this extraordinary precision barely suffices to detect the temporal signatures associated with subtle gravitational perturbations. The measurement process itself demonstrates how astronomical observations require technology that operates at the intersection of multiple physical theories governing phenomena, from quantum atomic transitions to relativistic spacetime dynamics. Deep space network antennas around the world coordinate observations that track spacecraft positions with accuracy approaching the wavelength of radio waves used for communication, approximately 20 centimeters for typical spacecraft transponders. This precision allows navigation teams to detect spacecraft velocity changes equivalent to the speed of continental drift, revealing how gravitational encounters influence artificial satellites just as they affect natural celestial bodies. The same mathematical principles that predict planetary perturbations also govern spacecraft trajectory modifications. demonstrating the universal applicability of gravitational physics across all scales of space exploration. Computer models integrating the gravitational influences of all major solar system bodies predict the long-term evolution of orbital modifications initiated by the Mars 3IATLAS encounter. These simulations reveal how small initial perturbations grow through resonant interactions with planetary orbital periods, potentially creating measurable effects that persist for thousands of years after the original encounter. The chaotic nature of gravitational systems involving multiple bodies ensures that some orbital modifications will amplify over time while others diminish, creating complex patterns of future planetary motion that depend sensitively on the precise details of the initial perturbation. Gravitational archaeology represents an emerging field that seeks to reconstruct the history of past encounters between solar system bodies through analysis of current orbital characteristics and their deviations from purely Keplerian motion. Just as geological features preserve evidence of ancient environmental conditions, subtle orbital anomalies encode information about gravitational encounters that occurred millions or billions of years ago. The techniques developed to analyze the Mars 3IATLAS encounter provide tools for investigating how past comet impacts, asteroid encounters, and planetary migrations have shaped the current architecture of our solar system. The encounter's gravitational echoes will propagate through computer models used to predict future planetary positions for spacecraft navigation, eclipse calculations, and astronomical almanacs. Every future mission to Mars must account for the orbital modifications introduced by this encounter, incorporating updated planetary ephemerides that include the effects of gravitational perturbations too small for human senses to perceive, yet significant enough to affect the precision navigation required for interplanetary spaceflight. These orbital echoes connect the ancient cosmic visitor to humanity's future exploration of the solar system. The mathematical beauty of celestial mechanics reveals itself through the precise quantitative relationships that connect microscopic gravitational influences to macroscopic orbital changes accumulated over extended time periods. The same differential equations that describe planetary motion also govern the perturbations created by passing comets, demonstrating the fundamental unity underlying apparently diverse astronomical phenomena. Each gravitational encounter adds another layer of complexity to the solar system's orbital architecture, while preserving the mathematical elegance that characterizes conservative dynamical systems operating under the influence of inverse square force laws. The vastness between Neptune's orbit and the heliopause opens before 3IATLAS, like an ocean of darkness punctuated only by the faint glimmer of distant stars, each point of light representing a sun with its own family of worlds orbiting in configurations that may bear no resemblance to our familiar solar architecture. As the ancient comet begins its long retreat toward interstellar space, carrying with it the gravitational memory of its encounter with Mars encoded in subtle modifications to its trajectory, the solar radiation that once drove spectacular outgassing from its nucleus weakens to levels insufficient to maintain the coma and tail structures that briefly made it visible to human observers across hundreds of millions of kilometers of space. The temperature of the comet's surface drops steadily as it recedes from the Sun, following inverse square relationships that ensure each doubling of distance reduces solar heating by factors of 4. At Neptune's orbital radius, approximately 30 astronomical units from the Sun, solar radiation provides only 1/900th the energy flux that reaches Earth's orbit, insufficient to drive sublimation of any but the most volatile compounds that might remain embedded in the nucleus surface layers. Carbon dioxide ice, which began sublimating when the comet crossed the orbit of Jupiter, returns to solid stability as surface temperatures plummet toward the equilibrium values that characterize objects in the outer solar system. The nucleus itself preserves within its crystalline structure a detailed record of thermal processing experienced during passage through the inner solar system, with temperature gradients that penetrated perhaps several meters beneath the surface, creating chemical modifications that will persist throughout the comet's return journey to interstellar space. Subsurface ice that experienced partial melting and refreezing during the closest approach to the Sun now exhibits different crystal structures and gas bubble distributions than material that remained continuously frozen, creating internal layering that encodes information about solar heating profiles and outgassing dynamics in permanent physical form. Solar wind pressure, though greatly diminished at these vast distances, continues to exert measurable forces on the expanding debris cloud that surrounds the nucleus, gradually dispersing dust particles along orbits that will carry them throughout the outer solar system over time, scales measured in millions of years. These microscopic grains represent the most persistent legacy of 3IATLAS's visit, creating a permanent addition to the population of interplanetary dust that permeates the space between planets while preserving chemical and isotopic signatures of interstellar material that originated beyond our solar system's gravitational boundaries. The comet's orbital velocity decreases continuously as it climbs out of the Sun's gravitational well, trading kinetic energy for gravitational potential energy according to conservation laws that govern all motion in conservative force fields. Yet unlike objects with elliptical orbits that eventually reverse direction and return toward their parent star, 3I Atlas maintains sufficient energy to escape solar gravitational influence entirely, following a hyperbolic trajectory that asymptotically approaches a straight line pointing toward its ultimate destination among the stars of the constellation Draco. Perturbations from the giant planets continue to modify the comet's trajectory through gravitational encounters that operate over distances measured in astronomical units, though these influences diminish rapidly as 3IATLAS moves beyond the orbital zones where planetary gravitational fields remain significant. The cumulative effect of these distant encounters introduces small randomized changes to the comet's velocity vector that will alter its arrival time at specific points in interstellar space by thousands of years, while shifting its ultimate trajectory through galactic space by distances comparable to entire stellar systems. The heliopore's boundary, marking the transition between solar wind-dominated and interstellar medium-dominated environments, lies approximately 120 astronomical units from the Sun in the direction of the comet's departure, requiring perhaps 50,000 years for 3IATLAS to complete the journey at its current velocity. This boundary represents not a sharp discontinuity, but a turbulent mixing region where solar wind particles interact with the interstellar medium through processes that create magnetic reconnection events, shockwave formation, and particle acceleration phenomena that demonstrate plasma physics principles operating on scales larger than planetary magnetospheres. Beyond the heliopores, 3IATLAS will enter the local interstellar cloud, a region of space characterized by particle densities and magnetic field strengths that differ significantly from conditions within the heliosphere. This interstellar environment contains approximately 1,000 atoms per cubic meter, primarily hydrogen, nitrogen, and helium, with trace amounts of heavier elements created through stellar nucleosynthesis and supernova explosions throughout galactic history. Though this density registers as perfect vacuum by terrestrial standards, it provides sufficient material to create drag forces that will gradually modify the comet's velocity over millions of years of interstellar travel. Cosmic ray intensities in interstellar space exceed those encountered within the heliosphere by factors of 10 to 100. creating radiation environments that will gradually alter the chemical composition of the comet's surface layers through nuclear reactions that transmute atomic nuclei and create exotic isotopes rarely found in solar system materials. These high-energy particles penetrate several meters into solid matter, creating radiation damage that accumulates over millions of years, while generating secondary particle cascades that can trigger complex chemical reactions within the frozen matrix of cometary ice. The galactic environment through which 3IATLAS will travel exhibits structure and dynamics that operate on scales vastly larger than individual stellar systems, with spiral density waves, supernova shock fronts, and molecular cloud complexes creating variations in cosmic ray intensity, magnetic field strength, and particle density across regions measured in hundreds of light years. The comet will serve as a passive probe of these galactic phenomena, accumulating within its nucleus a detailed record of interstellar conditions that reflects the chemical and physical properties of different regions within our galaxy's spiral arms. Stellar encounters during the comet's interstellar journey will occur at intervals determined by the local stellar density and the comet's velocity relative to the mean motion of nearby stars. The nearest star in the direction of 3IATLAS's departure lies approximately 20 light-years away, requiring roughly 4 million years for the comet to complete the journey if it maintains its current velocity throughout the transit. During such extended voyages, the probability of gravitational encounters with other stellar systems approaches significant values, creating possibilities for capture events that could incorporate this ancient solar system refugee into alien planetary architectures. The information encoded within 3IATLAS's physical and chemical structure will provide future observers, whether artificial or biological, with indirect evidence about conditions that prevailed in our solar system during the early 21st century. Isotopic ratios preserved in the nucleus ice carry signatures of solar wind composition, terrestrial atmospheric chemistry through cosmic ray interactions, and thermal processing during passage through different temperature regimes within our planetary system. These chemical fingerprints represent a form of natural archaeology that preserves environmental information across galactic timescales. The mathematics governing the comet's escape from our solar system demonstrate how local gravitational encounters connect to galactic dynamics through the hierarchical structure that characterizes gravitational systems across all astronomical scales. The same inverse square force law that determined the comet's interaction with Mars also governs its response to stellar gravitational fields during interstellar encounters, while galactic rotation curves and dark matter distributions influence the large-scale environment through which individual stellar systems move during their orbits around the galactic center. As 3IATLAS retreats into the cosmic darkness beyond our sun's gravitational reach, it carries with it a permanent record of its brief encounter with our planetary neighborhood, preserving in its modified trajectory and altered chemical composition evidence of the gravitational conversation that unfolded between this ancient wanderer and the worlds that orbit our modest yellow star in one spiral arm of the Milky Way galaxy.